Hello dear students. So here is a question of the day 3. Topic is rotational motion and it's a very interesting question. I have taken from Pathfinder. Check your understanding, question number 24. Check your understanding, question number 24, taken from Pathfinder. So it's a very interesting question. Actually, many students ask this question, right? And it's a common doubt of many students when they try Pathfinder book. So now the question first I'm explaining that two identical uniform cones are there, A and B, can rotate freely about their fixed central axis. Means this cone can rotate about these axes, right? So both have their own axis, right? And if cone A is rotated with a constant angular velocity omega A, means we are rotating from external agent with angular velocity omega A, how much angular velocity will cone B ultimately acquire due to friction between the cones? So due to friction between the cones, what will be the final angular velocity of cone B? So that is the question, right? Okay. So pause your video beta for 2 minutes. Try this question, right? So yes, you can give yourself at least 3 to 4 minutes. Is a very good question. Okay. Right. Now let's discuss the detailed solution of it. So first of all, what should be the approach of the question? So in this question they are saying one cone you are rotating by some external agent and B ultimately acquiring some constant angular velocity. So that is the question basically. Now the main point in this question is, if B is acquiring a particular angular velocity, then net torque on it must be 0 finally. So finally net torque on it must be 0, right? So that is the main thing. So our approach here should be that how I can find net torque on B. So the working part that I will do, I will try to find out net torque on B due to friction. So when B has acquired the final angular velocity, right? So now the approach is net torque on B about its axis should be 0 to acquire a particular angular velocity, right? So brainstorming angle, we need to do the calculation of torque due to friction on B due to A, right? So see beta, here this axis is fixed. It means as we are moving away from this axis, so more is the distance, more is the angular velocity, right? So near this point P, say that point is P. So near point P, velocity of surface points of the cone is less, and near point, say this is Q, velocity of surface point of A is more, and opposite is the case of for cone B, right? So it means there must be relative motion between the two surfaces, right? Okay. So now if you see, suppose now it's rotating in the shown direction. At point Q, velocity of the point is up the plane for cone A, right? But for cone B, velocity is up the plane, but it's very less. So frictional force acting on B is up the plane. Now do this comparison at like for points near point P. So near point P, if you compare similarly, for point on the cone of surface B, velocity up the plane, that is much greater than for velocity up the plane associated with the surface of cone A, right? So on these points near point P, frictional force acting on B should be into the plane, right? So that is the main thing, that frictional force direction is different at different points, right? So and in the question they are saying that pressing force is uniform. So we are maintaining a constant angular velocity of A. So net torque on A about its own axis is 0, but net torque on B about its own axis should be 0, right? So above for A it should be non-zero, right? It can be non-zero, no problem, because you are maintaining angular velocity. But for B, net torque has to be 0. So in this working, what I will do, I will calculate the net torque on B. So I am assuming any small element, right, at length L. So normal direction will be lambda into dl. So suppose lambda is normal direction per unit length. So then small friction I can write mu into lambda dl. So what exactly lambda I am writing? Lambda I am writing normal action per unit length. This, right? Okay. So now from any point 0 to L, from 0 to L I am writing a torque equation, right? So then I am getting this expression. So normal action into mu frictional force into perpendicular distance, right? Perpendicular distance. So L into this small r length is basically L sin theta. So similarly I am writing torque equation, right, from L to capital L, right? So now where I am choosing this point L, because I said na direction of relative motion is changing at some point. So there will be one common point which is having the same velocity for both the cones, right? So for both the cones are moving with same velocity, there has to be one point. So I am trying to find out that point. So now net torque to be 0, 1 is equal to 2 if I am doing. So I am getting small l is equal to capital L by root 2, that I am getting. Or in terms of radius if I want to write, so I can write small r is equal to r by root 2, right? So from here, from point Q, right, in cone B, small r is equal to r by root 2. So now relative motion is 0 at radius r by root 2. So velocity at B I can write omega into r by root 2, right? And for point A, I can write omega A into r dash, where r dash is this length. So total radius is r, total between these dotted lines, between these two axes, distance is r, capital R. So if I am saying radius is small r for cone B, then radius for cone A should be r dash, means capital R minus small r. So this I am doing. So what I am getting? I am getting omega A, right, in terms of omega B. So that I am getting omega A is equal to, oh sorry, so here root should not be there. So omega A is equal to root 2 minus 1, omega B upon root 2 minus 1. So that relation we are getting finally. Okay, so we need to find what? Omega B, right? So omega B will be root 2 minus 1 into omega A. So that should be our answer, right? So any step, if it is not clear, please post me in the your comment section, okay? Because this question is very important, right? Okay, thank you.